The workbench power supply unit. What makes it so special, and why does every electronics engineering enthusiast, hobbyist, or maker have to own one? Keep watching, you'll find out, but most of all, you'll learn how to make your own one. This video is sponsored by PCB Way, the user-friendly one-stop solution for making your printed circuit board designs come to life in the form of their quality-made PCBs. Aside from PCB manufacturing, don't forget that they're one of the only PCB companies who also offer unique fabrication services such as CNC metal machining, sheet metal fabrication, 3D printing, and even injection molding for whichever project you have in mind. All methods of which can be done with the material of your choice. They also do PCB assembly, which comes along with free shipping. So try them out by signing up with a head start of receiving a $5 welcome bonus coupon, uploading your Gerber file after getting your online quote, and submitting your order today. Check them out. Wire, a rectifier diode, male RCA connectors, female RCA connectors, female DC jack, Dean's connector, grounded AC cable with connector on end, alligator clips, single cell charging boards, DC to DC step down converter, SPST switch, SPDT toggle switch, dual USB power module, AC input connector, single plug AC outlet, battery tray, PC fan, temperature activated fan switch, blank perforated boards. Then, the two main modules to this project, numerical control DC 0 to 50 volt 5 amp step down converter, and an AC to DC switching power supply board with a 36 volt DC output. Additionally, you will need a handful of screws, some grippy rubber knobs for the feet. I chose Nerf dart heads, 4mm plywood boards, and lastly these two DVD shells which will make up the casing for our power supply. Here laid on this table is pretty much everything you will need in terms of materials and parts. You may also check the complete list of things you will need in the description below this video. Enough about the materials, let's get to making. And yes, if you're aiming to make a metal casing for your power supply, you will most likely need an angle grinder. So the first thing you're going to want to do is cut 4 of these metallic tabs which will hold the two shells together. These 4 will eventually be held on with screws. With these tabs being cut and drilled accordingly, it's now time to cut out areas on the upper and lower shells for components like the fan and battery tray to poke out through. So having made the cutouts on the two shells, you're going to make marks for holes through which bolts will be poking through, securing these two modules down. Depending on what style of grippy feet you choose, you may also need to drill holes for them. Some holes will also need to be made for the fan to be secured to the upper part of the case. And maybe even mark some areas where the cell charging indicator LEDs will sit. Now it's time for the drilling. With having drilled all of the necessary holes for mounting parts, let's epoxy up the areas where we shouldn't have gaps, and just for the general fix up of the two shells. Now that the two shells have all been sanded up, let's hit them with this light shade of marine blue. You most likely won't have to do what I'm making here, as you can probably pick these up for cheap, but as I did not have one of these lying around already, I'll make my own PC fan grill. These Nerf dart heads will now carry the weight of this power supply as the grippy rubber feet. Next up, from 4mm plywood board, you're going to want to cut out these two pieces, which will be formed to be the front and rear faces of the unit. First, focusing on the front, outline the areas exactly where each and every module and connector will be sitting in. Once you've sliced out these areas with your craft knife, you may leave this face looking as it is or change its appearance. Next, let's move on to making the rear face of the unit. At the back will sit an AC switch and of course the AC power connector. For a place through which the fan's air can be vented out, I drilled a whole group of holes just to the side of the switch and connector. Focusing back to the front face of the unit, let's mount in all of the components you see laid in front, except for this numerical control variable step-down converter. We will add that in as we start wiring things. You're going to want to epoxy up especially the ports, as they are for sure going to be yanked a lot. Adding PCBs to the backs of these modules and connectors is also another way to ensure stability, but also to assist in making solid connections between each component. Be sure to add a diode that can handle a good deal of current to the positive pole of the 12-volt DC jack. This way you'll avoid reverse polarity connections, as the diode blocks current in the other direction and basically makes this as an output only. Also be sure to make a parallel connection between the DC jack and the 5-volt USB module's inputs. For now, we're done with the face of the unit. Moving on to mounting this 220-watt switching power converting module onto the base. While we're at it, let's also mount this LM2596 DC to DC step-down converter to the base. If you wish to have the ability to power this unit with a DC supply such as a battery, then you may add an input connector like this Dean's connector over here to the side of the supply. So now on with the wiring. First, you'd want to connect the positive output DC side of the switching power converter to this pole of the switch. Then connect the middle pole of the SPDT switch to the positive input of the DC to DC step-down converter, and then hook up the buck converter on the negative DC side. Afterwards, wire up the AC side of the switching converter, plug it in, probe the buck converter with your meter, and then tune it till you get an output of 12.7 volts. To be able to see whether these modules are powered or not from the outside, desolder the surface mounted LEDs and simply extend the connections through some wires. Hook up your battery supply connector to the output terminal on the switching converter and the lower switch terminal, so that when a battery is plugged in, you just have to flick the switch and then the whole thing will come on. Now connect the 12-volt DC output side of the buck converter to the 12-volt input of the USB module. And since the DC jack is already connected up to the 12-volt side, we don't have to do anything with that. Desoldering this series connecting rail on the battery tray will allow us to have two separate battery charging terminals. Having it this way allows us to have a battery charging board for each cell. the cell charging board outputs all connected up to each pair of battery tray terminals, we can now mount it to the base. Now you may hook up the inputs of these modules to the 5-volt USB module. These extended 5mm LEDs will replace the current indicator LEDs on the charging boards. And with that little modification, we can now see the charging status of each cell that sits in the tray. While we're still dealing with the LEDs, let's hook up these power indicating LEDs. So here's a breadboard prototype I made of this analog heat activated switch circuit. You can see it in action here. And now let's pack it all down onto one circuit board. You can download the circuit diagram to this heat activated switch from the description box below this video. You can mount the board really anywhere. I decided to mount mine on top of one of the heat sinks of the AC to DC converter, along with the thermistor tucked well into the heat sink up behind the two transistors on this board. With a 12-volt source hooked up to the heat activated fan switch, all it really needs now is the fan. So finally, hooking up the main power supply module, be sure to connect up the inputs and be careful with the polarity as it has no input reverse polarity protection. Then connect the RCA plugs, or if you have banana plugs, to the output terminals of the module while keeping polarity in mind. And little did I know that the wire terminal block could actually be unplugged from the module and hooked up with the wires in a more convenient way, but at least now you know the smarter way to do it. Back to the cooling part of the circuit, let's install the 12-volt PC fan itself. With having taken care of the DC side, let's move on to the AC side of the circuit. Be sure to disrupt the hot wire line with this switch, and only when it's flicked on does the AC to DC module power up along with any other AC outlets, and make direct connections for the neutral line. Be sure to hook up an earth ground connection between the single AC outlet, the AC to DC converter, and the metal case of the power supply unit, all connecting to the ground pin of the connector. This step has to be done for safety, or else you could get an electric shock from the metal casing of the unit. Seems like I wasn't quite done with the DC side of the circuit, as I made a little mistake here. I made the single cell charging boards dependent on the 5-volt USB charging module's supply, when I should have instead powered the two modules through this 5-volt voltage regulator. Now the two charging boards can operate in full swing, consuming a constant current of 2 amps. So with everything being wired up accordingly, let's plug in the AC side and switch things on. It all seems to start up and function as it should. But before we close things up, let's just quickly tune the heat activated fan circuit. Tune it so that it only starts when the heat sinks get slightly warm. Hot glue is a good insulator to protect any module connections from ever short-circuiting. Now let's mount the front and back of this unit in place. And lastly, we'll close things up. So here let's make the two wires which will connect to the variable pins of the power supply unit. And on the ends of these two wires you have alligator clips which can connect to any component or circuit that you'd want to test.
And there we go, we have the two variable output wires. So to quickly run you through how this power supply unit works, it's simple. Pressing on set twice will get you to the overall power settings and some other features. This on-off button under the knob simply toggles the power output, and if you press set once, then press the rotary encoder several times, you'll be able to adjust the voltage and current independently. And what I mean by setting the current is you're setting the limit of how much current can be put out. And the text at the bottom tells you the input voltage to this module. So now let's test this lab bench power supply on a handful of gadgets and components. By selecting a lower digit of that specified value with the rotary encoder, you can get more incremental results when changing voltage and current.